All right, so
Okay,
please go ahead.
okay. Um, it's really a pleasure to be here and talk about processing and memory, which is a topic that I've been working on for a while with my research group and some colleagues, and it's just getting more and more important. And I won't spend much time motivating processing and memory. I think in this community, it's been in the air long enough and gotten enough attention that I think it's sort of widely known why there's interest in processing and memory, and the question is more about how do we actually make this work well and be beneficial. But just briefly, in the figures here, you can see how a representative high-end CPU and GPU family have evolved in terms of peak computing throughput in green and memory bandwidth in red. And so on the top, we have AMD EPYC CPUs, and in the bottom, we have NVIDIA GPUs going up to the Hopper series. And so you see that the performance is improving pretty significantly, and yet the bandwidth is falling further and further behind. So this is what's often called the memory wall, a term that incidentally was actually coined here at University of Virginia by Bill Wolfe and Sally McKee, who sadly have both passed away in the past few years. But what this means is that um, the processors are often sitting idle or having low utilization when running many of the important applications that we care about, from data analytics to LLMs. And yet there's an incredible opportunity because the real bottleneck is the very narrow I/O interface between the memory chips and the processor. And that's there for a variety of good technical reasons. But inside the DRAM, there's actually much higher data access bandwidth available. And if only we could get access to that internal DRAM bandwidth, we could do some really great things. And then on the application side, there's a further compelling reason, which is that oftentimes we're simply streaming through data, doing work that is very low computational intensity. And a great example is just filtering data to find items that are of interest, that meet some predicate. And so the driving applications that we're trying to accelerate with PIM are both memory bound and highly data parallel. And I should probably have added a third point here, very low in terms of compute intensity or arithmetic intensity. And if we can move the processing inside the DRAM or near the DRAM in some way, we have the potential for better performance, and we can save quite a bit of energy also by avoiding wasteful movement of data. Um, this slide I include because I think it's just striking how fast the data sphere is exploding. And this um, uh, in particular shows how some categories like human data, which includes genomics, but also all the kinds of sensors that people are starting to wear and use, and other kinds of sensor data that are rapidly expanding as we instrument the world around us with IoT and so on. And you see here how they're really rapidly outstripping business data, which at one time was considered one of the larger sources of data. And of course, we do all kinds of analytics on the data. A lot of it is very suitable for PIM. And more, these sources of data are also being used to train LLMs and also to query LLMs. And so um, the growth of AI has certainly created new opportunities for PIM. So just to give you a feel for what the opportunities are, this is a roofline plot. And for those who aren't familiar with roofline plots, on the x-axis, we have the arithmetic intensity on a log scale. So this is the operations per byte of data that we're fetching. And as we are on the left side, we're very low intensity. So 10 to the 0 would just be one operation per byte of data fetched. And on the y-axis, we have the performance on a log scale in teraflops. And so can people see my pointer? Otherwise, I can get the laser pointer.
Yes.
Yes,
Great.
we see it.
So over here in the upper right-hand quadrant, we see a variety of conventional processors. SPR is the Sapphire Rapids from Intel with HBM. Down here we have the AMD EPYC Turin. Up here we have IBM's Power 10. And then up here we have AMD and NVIDIA GPUs. And for computations that have enough computational intensity so that the processor can keep sufficiently busy while we're fetching the next bit of data, then we can reach a point where we're actually compute bound. And we can't go any faster because the processor is running flat out. And so these solid flat lines here are representing the max computational throughput of these processors. And then for lower arithmetic intensities, these slanted lines, you have the performance that can be achieved when we're memory bound. And the lower the arithmetic intensity, moving left on the x-axis, the lower that our performance is because we're more and more memory bound. And there's less and less work for the processor to do. And for each of these, we show the solid line is actually the throughput that we can achieve on a highly tuned matrix multiply, or GEM. And the dotted horizontal line of the same color is the matrix vector, or GEMV, throughput that we can achieve. And GEMV tends to be memory bound, and matrix multiply for at least a sufficiently square matrix is compute bound and can come close to saturating the processor. And then up here, we show what the all bank internal DRAM bandwidth can provide if we can connect enough processing power to the internals of the DRAM. And so here what we've tried to do is to normalize the number of DRAM banks that are available. We show this for both DDR and GDDR with 128 gigs of capacity. And if implementation didn't limit how much compute we could stuff inside a DRAM, and obviously, of course, it does. This is a limit study. But if we could do matrix multiply using the all bank bandwidth of the DRAM, we would get the solid line here. And it's lower than these high-end processors because the computing would be at a lower clock speed, and we've made some assumptions there. And then the corresponding dotted lines are what could be achieved with that all bank bandwidth inside the DRAM chips for GEMV. And so here is what you would get with GDDR6, whoops, and here's what you would get with DDR5. And then here's what you would get with an 80 gig HBM3. And that's limited because we're assuming here not that you have the all bank bandwidth, but only that you have the bandwidth that's available at the base die. And so the gap here between any of these slanted lines for the processors and what these all bank, hypothetical all bank upper bound curves give you for PIM show what the potential could be. And as you can see, it's like a couple orders of magnitude. So there's a huge opportunity there. And also, this shows the advantage of PIM over near memory processing, for example, in the base die of an HBM, assuming current TSV density, and shows you the benefits of truly having available the bandwidth coming out of all of the banks that are in the memory system. So I won't spend much time on this slide, but of course you might wonder, or at least old timers from my generation will often ask me, why PIM now? I mean, it was studied for decades off and on, and it didn't go anywhere. So what's different this time? And I would argue that both the opportunity and the level of pain that we're suffering are the motivations that give us the possibility of making PIM a reality now. The memory wall that was much discussed starting in the mid-90s, starting with the paper from Bill and Sally, well, actually even predating that, turned out to be a pretty porous wall because architects are clever people and they came up with all kinds of ways to hide the memory wall with better caching, with better prefetching, and so on and so forth. And technology scaling also allowed much larger caches, much higher associativity caches that further helped. And so it really wasn't worth such a major change in the ecosystem. Now we are finding that we're memory bound on many of the applications we care about that drive the modern economy. And they're causing the processors that drive a big part of the semiconductor economy to, to be stalled on many applications, have low utilization, which undermines the motivation to buy bigger and better CPUs and GPUs. And at the same time, we're starting to get a much better understanding of how we can build practical PIM. And so you've got both the pain and the opportunity that make this a ripe time to reconsider PIM. So I'd like to talk about a few architecture considerations, and I hope I'm not repeating too much that has come before in previous talks with that. Talk a little bit about PIM programmability, and then, if time permits, a little bit about a very, very particular kind of processing in memory, automata processing, which my group did some work on in previous years. So I think one of the important choices that the community needs to consider, and the discussions of PIM, I think, are not very clear yet in the research community about these choices, on whether we're trying to design a memory product that will be main memory, good main memory, performant main memory, high capacity main memory, but have PIM functionality as well. So it'd be compatible with existing and near-term memory standards. You wouldn't sacrifice much in terms of capacity or latency. And it would just kind of be like a premium memory part. So your applications that aren't written to use PIM don't really see any difference. They still have a good memory system. And if an application comes along that can benefit from PIM, great. They get some speed up and some efficiency. The challenge here, of course, is that building any kind of interesting logic in DRAM is very, very expensive in terms of area. And having some meaningful, sophisticated PIM in a main memory part is very difficult. And furthermore, for PIM to work well, you need the data in a layout that's compatible with PIM. And those transformations may require you to move a lot of data around, unless we can come up with some clever a priori ways to place the data in the first place. And so that may end up obviating a lot of the benefits of this approach. But I call that memory first. And then at the other end of the extreme is what I would call an accelerator first PIM. And this is not an either or binary. There's obviously a spectrum here. But at the other end of this spectrum, you're designing something that is fundamentally just another accelerator. It's an accelerator for data parallel, low arithmetic intensity applications that happens to use DRAM as the implementation just because it's well suited for this particular accelerator. And this accelerator might be visible over PCI or CXL so that you can still read and write data. In effect, being part of a NUMA memory system, but it's designed to be an accelerator. You're willing to sacrifice a fair amount of capacity to get an accelerator that has meaningful capabilities, and you're willing to sacrifice other aspects like the data layout may be in a way that makes cache fills and spills not very efficient. You can still access the data when you need it, but it's designed just for optimizing the accelerator capabilities. And I think it's useful to think in these terms when we're talking about what kind of PIM features and what we want and what kind of trade-offs make sense, because the trade-offs change quite a bit as you move along this spectrum. So maybe this is a good time very, very briefly, although I think this is largely redundant for this community, to give just a super brief dive into the internals of DRAM, just to make sure that we all are using the same terminology. So on the processor, you're going to have several memory channels, and each of them is controlled by a memory controller. And that's what sends the commands to the memory and schedules the commands in a way that tries to optimize the efficiency and achieved bandwidth of the DRAM. And with DDR, that's going to consist of 1 to 4 ranks. Don't really have the same rank concept with HBM. And a rank of DDR will consist of 8 chips. And I'm sure you've all seen these little green circuit boards with DRAM chips on them that are typically referred to as DIMMs that you put into a motherboard. In a laptop, the design of that stick is a little different, but it's the same basic concept. And I say 8 chips, but if you're supporting ECC, you typically need a 9th chip. But those 8 chips work in unison whenever you're reading a cache line or writing a cache line. And within each of those chips, you have 16, potentially 32 banks with the upcoming DDR standards, but you have 16 to 32 banks, and the banks have some ability to be in different states. So you can do some pipelining of getting a bank ready to access, then accessing that bank while you get the next bank ready to access, and so on. And often we'll refer to a bank, the way the memory controller thinks of a bank is actually as the logical bank in every chip on that rank. So if we're accessing bank 0, we're actually accessing bank 0 in each of the 8 chips in the rank. And for PIM purposes, it's sometimes useful to be able to talk about an individual bank, an individual physical bank on an individual chip. Within the bank, we have 16 to 32 subarrays that make up the larger bank. And when you do an access, not only are you accessing a particular bank, you're accessing one specific subarray within that bank. And the reason we have subarrays is just so that we're not activating as large of a bit cell array structure. The subarrays are typically 512-ish rows tall, and these rows are very wide, something like 4 to 8K bit lines. Sometimes people talk about those bit lines as columns, but in DRAM terminology, a column has a slightly different meaning, referring to a group of something like 32 bit lines that are activated together. So the terminology can get a little sloppy here. So each fetch to the bank interface will activate a row in a specific subarray in a particular bank, bring that row down into some sense amplifiers. This is an analog process. The sense amplifiers digitize the values that they're sensing from the bits and hold them in what's called the row buffer. And successive accesses to this row buffer will have much lower latency than closing the open row, writing the bits back, opening a new row, bringing those bits down and sensing them and latching them in the row buffer. So a page hit or row hit versus a page or row miss will have very different latencies. And then after when you're accessing a row, you'll specify the column, the group of bit lines whose bits you want to bring out to the bank interface, and the width of that interface that brings the bits down to the bank interface is quite narrow compared to the row. It's on the order of 64 bits for DDR, up to 256 bits for HBM. These, you could play with these parameters plus or minus a factor of 2, but our industry colleagues say that for layout reasons of the wires, the width that you can activate is somewhat constrained. And then I'm glossing over the fact that when we are accessing banks, we actually have banks grouped into bank groups. Within a subarray, it's actually made up of a bunch of smaller square mats, HBM, ECC, etc. I'm glossing over all of that for now. So there have been some early PIM products announced and one fully commercialized that implement PIM at that bank interface. So they can access data at a width, at a granularity of that global data line that's 64 to 256 bits, bring those bits out to a PIM compute processing element that's at the bank interface. And you can get the full all bank parallelism and the corresponding processing throughput. So Samsung's Aquabolt and SK Hynix's AIM were in HBM and GDDR respectively. There was physical silicon, but it wasn't widely commercially available. And then UpMem was a small startup that implemented bank level PIM in DDR. And they each had somewhat different designs for their processing elements. UpMem had the additional feature of a small scratch pad effectively for the main bank that uh, acted like a faster acted like a scratch pad. It was called the working RAM. Unfortunately, UpMem, even though they were selling product, and you could even, as an academic, get access to a cloud service so that instead of buying an expensive part, you could rent time on their cloud service, is no longer an independent company. My understanding is it's been acquired and all those services are no longer available, which is very unfortunate because it was a very interesting research prototype. So, of course, it's interesting to explore where exactly we might want to put the processing. We could put it at the bank level. That's much less intrusive into the design of the DRAM, but we could also put processing at the subarray level, either some kind of bit level processing at the interface to each of those sense amps in the row buffer for every subarray, or every two subarrays for reasons of the way the bit line, the row buffer is laid out. We could do that bit level processing in a digital or an analog way. My own group proposed one architecture for this called DRAM AP. Another approach would be, instead of having some logic attached to every sense amp, where the cost of that adds up super fast, if you think about how many bit positions there are in all the row buffers of all the subarrays of all the banks, you can't put much logic there. You could instead put a logic unit off to the side of the subarray. We called this design fulcrum, and this could be a more conventional processing unit with a bit parallel ALU that can even potentially do floating point. Bank level parallelism will give you lower parallelism because instead of being able to access the whole row buffer, you're only accessing that GDL width of 64 to 256 bits. But of course, it's much lower cost per bank, and therefore you could make those processing units more sophisticated. And then you could think about putting some kind of processing outside of the PIM, outside of the DRAM at the channel interface. So that could be in the base dive in HBM, or it could actually be in the memory controller or attached to the memory controller. My concern about near memory processing, or PNM it's often called, is that you're on the wrong side of that narrow IO interface. So you've lost a lot of the potential benefit of PIM. And then, of course, you have to think about what kind of functionality goes in these processing elements. What kind of data types can you work on? Can you support floating point? Is this purely a SIMD or vector type of architecture, or can the different, let's say, for example, bank level processing units do different things? There have been some papers on this subject. In the processing element, how much buffering or how many registers do you have? So if you're doing, let's say, a vector add on two rows in your bank, and you open row A and read out a little chunk to the bank level interface, and now you need to get the other operand from row B. So you have to close row A, open row B, get a chunk, bring it out, do the add. Now the result, let's call that C, needs to get written back to a third row. So you have to close B, open C. Now you can go on to the next chunk. So you close C, open A, and you end up never having page hits. It's just row thrashing. So you want some kind of buffering at the processing element to be able to read out a big chunk of data from A before you close it and start accessing B. And maybe you want to buffer a long set of the A plus B values into some sort of temporary place to hold the C values before you close B and open C to write those results back. And so the figures over here on the right are meant to show the bit serial subarray level, the bit parallel fulcrum. Here's the ALU that we proposed that sits off to the side of the subarray. And up here, we're showing some of the different places that you could put the processing elements. This is a good time to talk about address interleaving. So in conventional DRAM, one cache line is localized to a specific rank and a specific bank across that rank. And then different cache lines will be distributed in some kind of quasi-round robin fashion across different banks, ranks, and channels. And there are different interleaving policies. But the biggest issue that we're concerned with is that in the typical layout, different bytes, or maybe even nibbles, if you have an X4 DDR, will be in different chips. So when you read out a cache line with, let's say, 8 X8 chips, and by the way, when I said it's 8 chips per rank, I was assuming X8. There are other possibilities. But so for the first 64 bits of your cache line, you get 8 bits from chip 0, 8 bits from chip 1, 8 bits from chip 2, etc. That comes into the memory controller. And then the next chunk of data in the burst will have the next 64 bits until you've filled your cache line. And this is a nice linear streaming way that uses the full bandwidth of the DDR chips to fill a cache line. But it's terrible for PIM because your bytes of, let's say, an int are in different chips. And so for DDR, doing PIM would require some different way of laying out the data. This is less of an issue for the other kinds of DRAM. So in LPDDR, you can get an X32 LPDDR. And then GDDR and HBM will have at least 32 bits that you read out together. So at least that byte level interleaving is not a problem in this particular DRAM flavors. Although if you're operating on larger data structures, you may still have to worry about where the different words of your data structure lie. So PIM obviously wants at least your words, maybe even larger data structures, to be localized to a specific bank or subarray so that you can do meaningful computation. And so what's optimal for cache fills and spills is not necessarily good for PIM and vice versa. If you have to lay out the data in different ways, so that, let's say you have some data in a regular layout in DRAM, because that's how you read it in from disk, or that's how a previous stage of computation on the CPU produced the data, and that's not in a PIM-friendly format, and now you have to move data around to get it laid out in a PIM-friendly way. You just spend a bunch of time moving data and actually achieving no useful computation in the process. So that is a potential issue for PIM unless the subsequent PIM computation runs long enough to amortize the upfront cost of that data relayout. So just to illustrate a couple of these concepts, we've been working on an evaluation of how you might do online analytics processing on databases. So here, the transactions are done elsewhere, maybe on a different copy of the database. And then periodically, your analytics store is updated in a batch fashion so that when you're doing the analytics, you're not simultaneously trying to support all of the different transactional semantics. So you can do bulk data operations without interruption. And most of the tasks that you want to do are very memory bound. For example, scanning a table to find elements in a column that meet a predicate is the ultimate example, right? You're scanning a long array of data to find values that meet some criterion, either they're equal to some value or they're less than or greater than some threshold. Most of the values you're going to just look at and throw away. And You may do several of these scans and then join the results. The joins are also memory bound. Joins are more difficult, and so in one part of this work, we look at that issue as well. But the main point that I want to make here is simply that is first, that this is a great case study for PIM because it's a very natural fit. Now, interestingly, when we compare doing the filtering on one column of data and compare the performance of doing it with subarray level parallelism in every bank versus just bank level processing versus doing it out at the rank level, so every rank, maybe on the DDR stick itself, has a little processing unit, versus at the channel level, so that might just be at the memory controller, like the Intel Analytics Accelerator. What is the query time? And so we see speedups here as we go to PIM and bank level, because we're getting, let's say we have 4 ranks per channel, we're getting some speed up there, and then we have 16 banks per rank, we're getting some speed up there. And that's really, at this point, we're hitting diminishing returns and going to a more aggressive PIM with subarray level parallelism in this particular case turns out not to be beneficial. And so something as simple as simply filtering could be done at the bank level with just a very, very tiny bit of logic. Maybe that's a good candidate for an initial memory first product. We actually implemented this in DuckDB, and that's where these results are coming from. So we have DuckDB, full DuckDB running on the CPU, and then talking to our simulator, and we correct for the timing because the simulator is slower, so that we get a fairly accurate estimate of what a production database would do with this kind of scenario. So why is there diminishing returns when this task seems like it should be embarrassingly parallel? Well, after you've done the filtering, you have to get the resulting records to the CPU for some subsequent processing that is probably not PIM friendly, like sorting, for example. So you have to copy some of this, you have to copy the selected values to the CPU in the experiment that we run for processing that we estimated would be very poor on PIM. And that aggregation time is actually memory bound because you have to copy data before you can sort it or otherwise summarize it. And the actual potential speedup of PIM will also depend on the selectivity of the query. So if the query has very, very high selectivity and only sends over a tiny number of records, you may actually see speed up with subarray level parallelism. These results are the geometric mean across the full SSB dataset. Whereas if your query is not selective and you have to copy over a very large volume of data, then you're very memory bound. So we can address the next question, which is how to deal with joins by denormalizing the schema. Now, this works for some kinds of schema and not other more complicated nested schema, but the basic idea is that you pre-join all the tables into one giant so-called wide table. So now, rather than having to join different tables with something like a hash join, which is not particularly efficient, you just have one giant table, and joins actually just become filtering based on the predicate. So everything is now filtering. A denormalization can have some significant cost in terms of the size of the table, like up to 2x with SSB, but you get a significant speed up even with a conventional database that's not using PIM. And there are several commercial databases that do actually denormalize. And so this is a technique that's in use. And so what we found is that we explored some different degrees of denormalization. So how aggressive are you with denormalization? The more aggressive you are, the fewer joins you have. With D3, then you fully eliminate joins. And then we also looked at the benefit of denormalization with and without PIM. So the hashed bars are without PIM and the different levels of denormalization, and the solid are with PIM. And so you see there's some benefit from denormalization even without PIM, but you get the biggest benefits with PIM. And the geometric mean across the SSB dataset is about 6x speed up from PIM. And the reason it's not higher is because of this data transfer cost that I mentioned. So to further explore bank level versus subarray level and so on, for a wide variety of benchmarks, we developed a simulator that we call PIM-Eval, which is publicly available. There's the GitHub link. Feel free to contact me or just look at this paper that we published last year. You only need to simulate the PIM portion. Right now, we assume that the CPU portion is run on an actual CPU, and then you stitch together the timing. And then, of course, everybody wants to look at LLMs, and in this effort, we tried to explore other applications other than LLMs, which have been published on extensively, that might or might not benefit from PIM. So we tried to map a variety of compute kernels to PIM, and then we did some diversity analysis to see which of these are quite different from each other and which are too similar. And so out of this group of benchmarks, you could clearly subset and get rid of a few that are similar to others. And there's plenty of room to add to this PIM bench. And then we did some characterization. So here you see that if you have an accelerator first PIM, or assuming that you have to move data around to get it laid out in a PIM-friendly fashion, either way, you're reading data through the CPU out to PIM-enabled memory. And for many of these applications, the data movement cost is a very large fraction of the overall end-to-end processing time. And then for some stages where you need to do some kind of aggregation of partial results, or maybe you need to do a step of summarizing or rearranging data to farm it out for another stage of PIM processing in some kind of bulk synchronous manner, the host can be a large portion of the execution time as well. So, for example, in radix sort and random forest, we see that it's host dominated because of these bulk synchronous host coordination stages. Whereas for something like vector add, unsurprisingly, there's very little compute, so it's highly limited by data movement. And then we also characterize the read-write mixture here. And then we did another version of a roofline plot where we looked at the potential bandwidth of some processors, like pink is the EPYC, and here we did the NVIDIA A100, and compared this to the potential speed up of some different PIM architectures that I described earlier. The lines are the sort of upper bound that could be achieved in an ideal case, and then the x's plot where specific benchmarks fall, and the x's are color-coded to the corresponding processor. So you see here for vector add, for all of these, we get relatively close to the peak for the PIM architectures. And we're way, for like the EPYC or for the GPU, we're way below the knee of the curve for those conventional processors. Then for something like histogram, we're further away from the ideal case. And so there's additional stages of processing there that become a bottleneck. So with the current implementation we have, which is certainly probably amenable to further tuning, here you see compared to a CPU, what the speed up is for the bit serial, fulcrum, and bank level PIM techniques. And we included benchmarks here. We intentionally included benchmarks that are hard for PIM. So I would argue that the geometric mean is actually not very meaningful because we're not trying to make the architecture look good. We're trying to show a range of behaviors that might stimulate further research, like how could you make histogram faster? But you see here that for certain types of applications, bit serial is great. And for others, like those involving multiplication, which is not very amenable to bit serial, the CPU is not as good. Then we did the same for GPU, and it's harder for PIM to compete with the GPU. It has to be an extremely data parallel application. And then we see that kind of proportional to the speedups, that significant energy savings are possible. The other thing that I want you to take away from these is that the performance, when we look at just the kernel by itself, assuming the data are already set up for PIM, the performance is way higher than if you first have to copy data into the PIM, which would be the hashed bars. And if you compare the solid and the hashed bars, for many of them, you see that there's a significant drop-off in performance. And here we see, unsurprisingly, that for bank level PIM, the GDL width matters. So if we just magically assume we can vary the GDL width, the chunk size that we fetch out of the subarray out to the bank interface, the speed up is pretty much proportional to the GDL width. In the interest of time, I'm going to go a little faster now. So for bit serial, what we were evaluating up to this point was digital. And based on the DRAM AP architecture that we proposed in that paper last year. There has been a considerable amount of work on analog PIM. And the appeal of the analog bit serial subarray level PIM is that the computation actually happens when you activate multiple rows simultaneously, and they each contribute their charge onto the same bit line. And there's some interaction there that allows you to do a very primitive Boolean computation. And from that, you can build up more sophisticated operations. And, if you have a suitable PIM architecture and a suitable base primitive like majority, you can implement fully featured computation. It's computationally complete, although multiplication and floating point will be much, much harder because the primitives that you have in the analog approach are even more constrained than in the digital DRAM AP approach that we evaluated. But it is logically complete, and there is no area overhead to put logic next to every sense amp, although you need some extra decoder logic and so on. And there is some additional power overhead to activate multiple lines simultaneously, but it's pretty modest. Now, there has been some recent work suggesting that there may be some other area costs if you have to have dual contact cells that can touch multiple bit lines simultaneously, but overall analog is very promising. And I'm going to skip over the other digital bit serial that we looked at, but I think there's still a lot of room to do an interesting comparison between digital and analog bit serial. I think it's a very interesting direction to pursue because analog is so area efficient and yet requires a lot of work. So the lessons that we've learned so far are one that I didn't point out earlier, but as the GDL width gets wider and you can do more words of computation per fetch out to the bank interface, you lose some of the benefit of the subarray level parallelism, especially the Fulcrum approach. And so I would argue that a wider GDL actually kind of undermines the potential benefits of the Fulcrum approach. Good speed up is possible, as I showed, but as GPUs continue to get better and better and incorporate more memory bandwidth, it's going to be harder and harder for PIM to keep up with them. But there are also significant energy efficiency benefits, and that putting the logic in DRAM may be more scalable as you build out a larger memory network rather than the amount of memory that you can directly attach to the CPU or the GPU. So I want to talk a little bit about programmability, and I don't think we'll get to the automata stuff, and that's fine. So actually, I'll just briefly cover these slides. So of course, whenever you're mapping a new algorithm to a novel architecture, you have to think about whether there are better ways to do it. So for example, the typical way that we think about a matrix vector multiply is that you take your input vector and you do a dot product with every row in your matrix. And each dot product gives you one element in your output vector, as shown on the left. But you don't have to do it that way. And the alternative would be to take one element of your vector and do an element-wise multiplication with a column, and that produces a partial result column. And for every column in the original matrix, you get a partial result column that you accumulate into an eventual output column. And depending on the nature, on the aspect ratio of your matrix and the constraints of your PIM architecture, the approach on the right may actually be better. So in particular, if your matrix is tall, or if it's skinny really in any dimension, doing these row-wise tasks may not be a good fit for the structure of the parallelism in the PIM. And operating on very long columns may actually be more suitable. And this ends up being particularly true for the bit serial row-wise subarray level approach, whether it's analog or digital. The approach on the right will typically be better. And I'll skip over this. So if you have a compiler, which you definitely want to make PIM programming tractable and not have people writing low-level, basically assembly code, or even building up your typical like add operation from low-level majority operations, you want a compiler. And down here at the bottom, after working with a compiler team to automate some exploration of this, we found that changing to that column-oriented approach on the right of that previous picture that I showed you gives you a significant speed up compared to the row-oriented. To do all this, we found that it was useful to come up with a sort of generic API that represented a sort of generic, you could think of it as a PIM ISA with your typical operations like add, multiply, et cetera, that would be portable across all the different PIM architectures that you might want to explore. And then we're working with a compiler team to treat this as the virtual ISA that you target with your compiler. We're working with Vikram Advai's group at Illinois. But what this PIM API lets you do is when you come up with a new PIM architecture, or let's say you want to compare bit serial to bank level, you have the same program written to the same API, and then underneath the covers, every time you add a new PIM architecture, you just have to port the small set of API calls to the lower level primitives that are in the native architecture that you're implementing. And that's a much more tractable thing. Now, it is true that if you compile the program once, there may be different trade-offs that, even though your program is perfectly functional, mean that you might want to change the algorithm for different architectures. And again, that's much easier to do if you have a compiler and a nice virtual ISA. So an example of needing to change the algorithm is that for bank level, you might want the traditional row-oriented dot product approach, whereas for subarray level bit serial, you might want the column-oriented partial result approach. But here is an example of writing AXPY, which is simply a scaled vector multiply. You're just multiplying a value x, sorry, a value x times a scalar a, and then adding it to y, AXPY. And here's what it would look like in the PIM API. And the API also includes all of the calls that you would need to allocate the memory and copy the memory to the PIM device, and so on and so forth. So I already talked about compiling. Compiling obviously gives you a huge reduction in lines of code compared to the low-level assembly-like PIM API. And kind of to start to wrap up, I think the software ecosystem and portability considerations are just as important as the hardware innovations. So for example, a good programming model and good libraries, good compilers, I should have mentioned, were key to GPU success. right? That is part of what it made it relatively easy. I'll put the relatively maybe in air quotes because it was a bit of a rough time in the early days of GPUs, but that's what made GPUs so successful. And now that there are so many robust libraries supporting AI, you can use a GPU for AI without really having um, to write low-level GPU code. And we're going to need something analogous for PIM to be successful. And the portability here is key because there will probably be a wild west of different PIM architectures that have different ISAs, different architectural features, and so on. Overall, I would say it's not clear yet which of these PIM architectures is most promising. Bank level is clearly the easiest to incorporate inside the DRAM compared to subarray level, but bit serial offers significant speed up. In many cases, but even if you have some multiplication, as long as the multiplication isn't dominant, the bit serial can still be compelling. And the area overhead of logic in DRAM is high, but the speed up potential outside of the DRAM in a near memory type of architecture, whether you put that in the base die of an HBM or in a CXL switch or on the circuit board of a DIMM, you're on the wrong side of the I/O interface. And I would argue that while there may be benefits to P&M approaches, you're really missing the huge opportunity of accessing that all-bank bandwidth. Lots of open issues for research. System integration is going to be essential to the success. We need to work out how to communicate with the CPU, how you invoke a PIM program, what the locus of control is for running the steps of computation in that PIM program. Is the CPU core doing it step by step? Do you have a PIM execution unit in the memory controller? Kind of like the Aquabolt and AIM approaches. Do you have a core next to the bank where you download a program and then it runs autonomously, like with UpMem? It's still the Wild West in that regard. Memory allocation, making sure that things are aligned nicely with rows and dealing with avoiding row thrashing, all these kinds of layout issues will be very important. We have to worry about memory consistency, maybe cache coherence. What if you have some data in the last level cache or the L1 cache, and now you want to do PIM computation on a larger array in memory? You obviously want to make sure that you have the most up-to-date data, which probably means some cache flushing. How do you support multi-tenancy, and so on and so on? And basically, where can PIM provide a meaningful value add that is a nice complement to what CPUs and GPUs will provide according to their roadmap for further development? And then we can't lose sight of embedded systems where the processor may be much more constrained and PIM may actually provide great opportunities. So I'll skip over the automata processing and just wrap up. I think that PIM shows great promise, but we are still wrestling with the chicken and egg problem of what the market is that will really motivate a company to spend the money to introduce a PIM product. GPUs didn't have this problem because GPUs already had a market and they could just add some features and some software interfaces. PIM is going to require something more significant. And I think the remaining bullets on this slide are pretty self-explanatory. I've already talked about the importance of software and some of the many open issues that remain for research. And so I'll stop there and just thank the team that's been working with me over the past few years on this PIM research. Thanks.
All right. Thank you very much, Kevin. So let's stop the recording and get
Subscribe the channel to get the instant updates on our webinars.